last class we talked about potentials and we also found out the potential difference between 2 points R1 and R2 because of a uniform infinite line charge. Okay. So, we said that for the uniform infinite line charge you cannot use infinity as the point of reference. So, we have to use some other point in finite value of R as a point of reference for 0 volts and measure all the other voltages at other points with respect to voltage at that 0 which is not at infinity. Okay. So, you hopefully you remember this expression V of the potential difference between the 2 points R1 and R2 if you move from R2 to R1 was given by this expression in which I am assuming that R2 is greater than R1. Okay. Let me say this rho L by 2 pi epsilon 0 is equal to some 10 volts. Okay. R2 by R1 of course has no dimensions because it corresponds to the ratio of the two distances or two radial distances. So, you have the potential difference being given by this expression and for simplicity let us consider this rho L by 2 pi epsilon 0 to be 10 volts. Okay. From this expression you can calculate what will be the value of rho L and it will turn out to be 556 picocoulombs per meter. Okay. Pico standing for 10 to the power minus 12. So, it will be 556 picocoulomb per meter. Now, let us say I want to write down or I want to find the radial distances which all correspond to the same potential with a potential unit of 5 volts, that is I want to find out the constant potential contours which all differ by 5 volts. Okay. So, my question is what should be the ratio of the radii R2 and R1 in order to obtain that 5 volt potential differences, which of course depends on which part R2 or which radial distance R2 I will be selecting as the reference or the 0 potential. Okay. If I substitute this 10 into this expression and then say that with certain value of R2 I am going to consider that as 0, then the voltage at this particular point R1 should be equal to 5 volt, right. So, at R2 whatever value of R2 that I choose, that will be the reference, at that point the voltage will be equal to 0. So, if I move along from R2 to R1, what should be the value of R1 in relation to R2 such that the potential there will be equal to 5 volts. Okay. And remember that potential rise will happen only when I move against the electric field. So, I have V of R1 equal to 5 volt, I can substitute here this into 10 volt and then there is a log of R2 by R1. You can solve this expression and you will see that R1 will be equal to R2 by 1.65. Okay. So, the ratio of R1 and R2 should be such that R1 is equal to R2 by 1.65. So, because there is a 1.65, let me arbitrarily choose R2 is equal to 16.5 centimeter as the point of 0 voltage. Okay. So, I have the infinite line charge over here and along this radial distance at some 16.5 centimeter I am going to choose this as the point of 0 potential. Okay. In fact, it will not be up and down, but it would rather be along a circle. So, at all the points which are radially equally which are radially at 16.5 centimeter, the potential will be constant and the constant potential contour will actually be a circle in this case, okay, having a particular value of radius. So, if I choose this 16.5 centimeter as the 0 voltage constant potential contour, what will now be R1 such that the potential there should be equal to 5 volt. It turns out that if R2 is equal to 16.5 centimeter and if I want to obtain 5 volts, then R1 must be equal to 16.5 by 1.65, which is 10 centimeters. Okay. I am calibrating everything in terms of centimeters. This is the infinite line charge, okay. This is at 0. So, at some point 16.5 centimeter radial distance away from the line charge, the potential is taken to be 0 and if I now take R1 is equal to 10 centimeters, that is if I take this as 10, if I go 10 centimeter from the origin, the potential here will be 5 volts, okay, because this will be R1 is equal to R2 by 1.65 and R2 is 16.5 which I have taken as the arbitrary point of 0 volt. So, at R1 equal to 10 centimeter from the origin, the potential is 5 volt. You can again try to find out where the potential gets incremented by another 5 volts, that is I want to find out what would be the value of R where I get 10 volts and that value will be 10 centimeter by 1.65, right. So, because these ratios that you are looking at, the ratio between these 2 points is 1.65. Similarly, the ratio between these two must also be 1.65, and the value of R from the origin where the potential will be 10 volts is given by approximately 6.1 centimeters. Okay. So, it would be around 6.1 centimeter. If you continue doing this at different values, you are going to get different potentials, and the potential keeps on rising, and the potential goes as the logarithmic value. Okay. For example, at 6.1 by 1.65, which is approximately 3.7 centimeters, the potential here will be equal to 15 volts. The potential becomes 20 volts at 3.7 by 1.65, which is around 2.22 centimeters. The potential becomes 20 volts at 2.22 centimeters from the origin, okay, and at 16.5 it is 0. All right. Suppose I consider a metal line or a metal surface, okay, which I am going to cover at 16.5. I cannot show you the metal surface over here, I am showing something like this. So, this is the center where I have the central line, okay, the infinite line charge, and I am going to consider a metallic surface around this 16.5. Okay. At all these points around the surface of this metal, which is located with a radius of 16.5, the potential value will be equal, and the potential value will be equal to 0 volt, okay, because that is what I have taken as the reference, and we know that a metal can be used for grounding purpose. So, the metal is grounded in the sense that the potential at that surface on the surface will be equal to 0 volts. However, and fortunately that does not change anything about the problem, in the sense that the potential at the center of the line, or sorry, the potential at the 2.22 centimeter from the origin, if I am going to put one more metal here, the potential here will still be equal to 20 volts. Okay. Such an arrangement of two metallic surfaces which are concentric with respect to each other is known as a coaxial line. Okay. Of course, what I have not told you is that coaxial lines actually have some amount of thickness here, okay, for both the inner and outer radius, but for our purposes a very simplified understanding, this kind of a picture is sufficient. You take an infinite line charge or essentially a long line charge and then neglect all the fringing effects that is happening at the end, okay, and for this line charge you now take two metal surfaces. Around the two metal surfaces you place them, one at 2.22 centimeter and one at 16.5 centimeter. Take the 16.5 centimeter as the reference and assume that this 2.22 centimeter thickness that we have is so small that the charge distribution around this 2.22 centimeter cylinder can be approximated by a line charge density at the center of the cylinder. Okay. This is an approximation that we are making, but this is an excellent approximation for practical coaxial cables. Okay. For a practical coaxial cable, one can, to the first approximation, think of the inner conductor as replace the inner conductor by a line of uniform line charge density, and the surface will essentially be the grounded or the zero reference potential. Okay. And all other points inside the surface, inside the coaxial cable, the potentials will be as we have already calculated. Okay. Now, if I ask you that for the same coaxial line situation or for the same coaxial line problem, that outer at 16.5 I have the zero potential located by grounding that coaxial cable, but the center conductor potential is actually at 20,000 voltage, which is about 1000 times higher than what I have shown in the problem. Can you now guess what will be the line charge density in order to potential? The line charge density would obviously not be the same as 556 picocoulomb per meter, right. For a 556 picocoulomb per meter with this configuration of 16.5 outer radius and 2.2 inner radius coaxial line, the central conductor will be at a potential of 20 volts. Now that we have increased from 20 to 20,000, what will be the new value of rho L? You can easily calculate by going back to this rho L by 2 pi epsilon 0 expression, or you can also calculate it by observing that you have increased the potential by a factor of 1000, the charge should also essentially increase by a factor of 1000. Okay. You can show that for 20 volts at 16.5 centimeter to 2.22 centimeter coaxial line radius, the line charge density and the medium is all related according to this expression. And if you now say that the potential has to be 20,000 volts inside the conductor, rho L2 will be the new line charge density, that would be 2 pi epsilon 0 ln. This particular thing has not changed, right. This is still the same 16.5 and 2.22 centimeter. So, you can divide one by the other and show that rho L2 will be equal to rho L1. In other words, the new line charge density that we are looking for in this 20,000 volt scenario is 556 nanocoulomb per meter. Okay. Here again you can see the appearance of picocoulombs, nanocoulombs. The amount of charges that are there or the charge density is actually very small, because picocoulombs and nanocoulombs are what you actually see in practice. We have seen that 1 coulomb is actually a very large quantity. Okay. Here are some of the other field distributions that I am going to show you. I hope that you can follow these new field distributions. Okay. Suppose I have a positive charge here, a point charge, and a negative charge that is situated here. We have not really calculated the electric field because of this configuration. Okay. We will calculate the electric field shortly later, but for now you can kind of imagine that if I do not have the negative charges, then the electric field lines would have all be located radially away, right. They would all be radially away. However, the charges for the negative point charge would all be radial, but they would all be pointing inwards, right. Now that we have a positive and a negative charge, what happens is that the electric field line will begin from the positive charge. Okay. So, it will begin from the positive charge and then end on the negative charge, and away from the positive charge to the vertical direction, here the charge is still radial, whereas for here the charge would actually not be radial. You can show that the constant potentials would also change. The potentials would now be constant potentials, will all be now contours, right. They would all be spheres of a particular value. However, they themselves will have to change, because the field gets weaker down here, the spheres are not exactly nice, the centers are not situated at the charges themselves. So, these are the constant potential lines. Okay. How about the field lines? Field lines must be perpendicular to the field, perpendicular to the potentials. Okay. So, there is one potential which is in the center, okay, like this. These are the potential contours. The field lines would of course all be parallel to the contours. Okay. The field lines are all like this, sorry, the field lines are all, for the positive charge they are all going, so for the negative charge they are all going inside. Okay. So, outside the field lines are all still radially directed away, and then they start to bend towards this one. We will actually derive the electric field, and I will give you a MATLAB way of solving or finding or sketching this particular electric field sometime later. What would happen if you had both positive charges? Then the charges would not be meeting together, because both are positive charges, the charges are they are actually going to repel against each other. Therefore, the contour lines would all shift, the contour lines would be like this, the fields would all shift away from each other, right. The fields would be away from each other. Okay. Now, there is one very interesting application of producing very high voltages called Van de Graaff generator. Okay. A Van de Graaff generator can produce high voltage charges by high voltage applications. Okay. How does a Van de Graaff generator look like? It actually is very simple. Conceptually, there is an insulating piece covering up a metal, and then there is a big shell, okay, of a large radius that is made up of the metal. The metal plates are also brought together to connect them to a flat surface, on a ground, and then there is a insulating material made up of rubber or something, which is put on a pulley on a conveyor belt kind of a thing, and then made to rotate around or made to go around this belt, okay, and they are connected here like the belt, and these are energized by applying a potential. Okay. These are energized by applying a potential, and a motor that you can think of will actually perform the operation of carrying the belt around the loop. Okay. And there is a brush here which will transfer the electric charges that are generated at the base, they will transfer that to the metal shell. Okay. So, the metal shell gets charged and all the charges that are sitting at the bottom will be transported away, and from the contact of the brush, this is the brush with the insulating material out here, will transfer this. This is essentially what the old type of experiments that we used to do, take a glass rod and then rub it over a dry cloth, bring it very close to a comb which has been, you take a comb and then you comb your hair and then bring the two together, they would repel, they would attract. These are essentially the same kind of experiments, except that these are generated to generate, these are designed to generate a large amount of charges, okay, and large amount of voltages. They can handle voltages around 50 to 100 kilovolts here. Okay. So, what would be the charge configuration or the field lines around this Van de Graaff generator? We have a shell which is all covered up on the surface by positive charges, and we know that these positive charges are going to generate field lines which all will be radially directed away, right. So, the field lines, if you were to look at, because on the top of the shelf you are going to see that the field lines, there is a brush, I am just showing that this is the metal shell and there is an insulating material here, the charges are all located with a positive sign here, I am assuming that they are positive. So, the field lines are all going to be radially away like this. Okay. So, the field lines are all radially away this way. Now, if I bring a metal plate, I bring a flat metal plate up here, what will happen to the field lines? Well, because on the metal in the static electric field, the potential will all be constant, and the metal, because there are free electrons in the metal gets charged to the opposite polarity. So, some of the field lines will converge onto the metal. Okay. So, the sum of the field lines will converge onto the metal, and you can see that the fields are now bending. Okay. Suppose on the same metal shell, the Van de Graaff generator, I put a corner, okay, a metal plate with a corner like this. What would happen? Will the fields get attracted to the corner or the fields will not get attracted to the corner? Remember, if this metal gets charged, right, that becomes an equipotential surface, then the field lines must always be perpendicular to the equipotential lines, right. So, that is what we saw in the previous case. You had a point charge, all the field lines were radially directed away, but the constant potentials were all spheres, and on a surface of a sphere, if this is the electric field and this is the contour of the constant potential, they are orthogonal to each other. Okay. So, this was something which probably I missed telling you in the last class, but essential thing is that electric field lines and the constant potential lines or the constant potential contours are always orthogonal to each other. Okay. That was evident in the pictures that we drew in the last field line configuration. Okay. So, with the metal plate brought near the shell, what will happen to the field lines? The field lines have to perpendicularly land on the metal plate, right. So, therefore, and they cannot do this by a straight line, right. So, because of the perpendicular, because of the curved nature of this plate which I have introduced because of the corner, the field lines would all land perpendicularly on the metal surfaces, but none of them would get attracted to the corner. So, the field here is weak actually. Okay. On the other hand, instead of a corner, I put a wedge. Okay. If I put a wedge, then what happens is that the field lines are all going to be landing on the wedge. Okay. So, the field lines get attracted to the wedge. However, the field lines avoid the corners. What happens if on this metal shell I place a metallic edge? Okay. If I place a metallic edge, what happens to the field? Well, this is a very, very special case of a wedge, in which you take a wedge, okay, and then you bring them together. What happens is at the base, the field lines would all converge and the field at the edge will be very, very intense. Okay. So, the field at the edge will be very intense. The field here is intense. So far we have talked about point charges, we also talked about line charges. I did not give you an expression for the potential at any given point where I have a collection of charges. Okay. These are not infinite charges that I am talking about, or the charge densities which are uniform but extend all the way to infinity. These are a collection of charges that I am looking at. Okay. So, for this collection of charges, what would be the expression for the total charge? Total charge will be q, I know is the total charge. If it is a line integral or a line charge, then the total charge will be rho l dl. It would be integral over the surface if it is a surface line charge or a surface charge density. It would be an integral over the volume if it is a volume charge density. This is a volume charge density, a line charge density and a surface charge density. So, the potential at any point in space V of r is simply obtained as the superposition of the potentials by considering them to be point charges. Essentially, it is saying that the summation becomes integral and you replace the charge q which was there in the point charge potential calculation by the appropriate integral. Okay. So, the appropriate integral with a more general case will be the volume charge integral divided by the integral has to go not only on the sources, but there is also radial distance involved. Remember, there is a radial distance from the source point to the field point. So, this would be the expression for potential, assuming that I have already chosen a point of constant potential. Okay. So, this is the expression for the potential of a continuous charge distribution. Okay. Well, we originally said that the potential difference between 2 points delta V is actually the negative of the line integral, right, some point from the initial point to the final point. Okay. Is there a way I can turn this equation around so that I can express electric field in terms of the potential function? Is there any advantage of doing such a conversion or asking for such a relation? Yes, if I perform this, if I invert this relationship from potential to electric field and express the electric field in terms of potential function, then I can calculate electric field by making practical measurements of the potential, right. So, I normally what happens in electromagnetics problems is that I do not know what is the electric field or what is the charge distribution. In fact, those are the quantities that one has to calculate them. What can be measured is the potential because of this charge distribution or any other I mean potential because of the charge distribution. So, I can make the measurements on the potentials easily, and from there I should be able to construct the electric field. If I can find a recipe for doing that, then my life becomes so simple, right. I do measurements and then maybe I interpolate them and then I can find out what is the electric field. Okay. This operation of going from potential to electric field involves introducing a new operator called gradient. What is a gradient? Imagine a surface, imagine the surface of a hill, or just imagine a hill out. Okay. Now, if you have ever climbed a hill, then you know that at any point you stand, okay, assuming that all the paths are accessible to you, at any point you stand, you normally want, if you want to climb to the top, you are going to find where the slope is actually changing at its maximum, right. So, if I have this particular smooth curve here and if I am standing at this particular point, I will try to find out where the potential is, where the slope is maximum, because imagine at this point I am standing, I will move horizontally like this, but the slope is not changing if I move along this line, right. The slope does not change. If I move downwards, the slope changes, but the slope change is not what I am looking for, right. I mean, I am looking for to climb up, and there is a direction. If I actually drop many such points here, I will find out that only along this particular direction towards the up direction, the where the potential is changing, I can, if I follow that path, okay, if that path is accessible to me, if I follow that path, then I will reach the top very easily. Okay. So, this is something that you might have observed in practice, but you might not have seen that there is a mathematical way to capture that phenomenon, and this mathematical way to capture that phenomenon is to give this value, or if to give this quantity of the derivative along a particular direction, or sometimes called as directional derivative, a name, and this name is gradient. Okay. To introduce you to the gradient, let us go back to one dimension. This is the distance delta x that I am considering. Okay. I move along this one, and let us say the electric field is directed along the same direction, that is opposite direction, but along parallel to this delta x. Okay. what will be the total change in the potential here? The total change in the potential will be delta V, and if you look at this, the delta V will be equal to electric field into delta x. There is a minus sign here because minus we are moving against the field. So, the electric field can be written as minus del V by del x. We have seen this earlier, right? We have seen this minus del V by del r, and then del r was taken to 0, but here I am trying to make it little more precise. So, what field actually I have got? The field that I have actually obtained by doing this operation by moving along delta x is actually the x component of the field. Okay. And in the limit of delta x going to 0, the electric field at this point is actually given by minus dV by dx. Okay. However, in general the potential could be a function of all three components. V would be a function of x, y and z. In that case, I have to replace this dV by dx by the corresponding partial derivative. Okay, by the corresponding partial derivative minus del V by del x. So, I can actually build up other components of the electric field by following this idea, right. So, I have the total electric field given as partial derivatives. So, this would be x hat, there is a minus sign which is common to all of them, minus x hat del V by del x plus y hat del V by del y plus z hat del V by del z. Okay. So, this particular expression in which I have managed to invert the integral relationship. See, this was the integral relationship that I had, which would give me the potential difference given the electric field. In this expression, I know what is the potential difference or the potential function. From there, I am extracting the electric field. The quantity that is sitting here in the right hand side of this one is more commonly expressed as minus gradient V, where gradient is an operator. Gradient is a operator which is defined as x hat del by del x plus y hat del by del y plus z hat del by del z. Why am I saying that del is an operator? Because del by itself, if I write like this, has no meaning. This is like saying, hey, what is the meaning of d by dx, right? If I write down this d by dx, unless I attach this one with some function of x, there is no point in just writing d by dx. Similarly, if I just give you del operator, there is no point in that one. In fact, in the d by dx yx f of x example, d by dx is called as the linear differential operator. Okay. Similarly, you have directional dependent, that is the different partial derivative along x will give you the x component, partial derivative along y will give you the electric field for the y component, and del by del z, that is partial derivative along the z, will give you the z component. And the operator does not make sense until I attach the potential function to this one. And why am I taking negative? Again, it has to do with potential rise. So, you go against the field, you are increasing the potential. Okay. So, this operation is called gradient, and the electric field is given as, in some textbooks you actually use the word grad. What is important to note is that grad and del are essentially one and the same. Grad is more descriptive perhaps, but the commonly used description is to use a del operator. Okay. So, electric field, which is a vector quantity, is given by the negative of the gradient of a scalar quantity. Okay. So, you have to be careful here. You have on this right hand side of this expression potential function V, which is a scalar, and I am applying some operator to this potential function so as to convert that potential into a vector quantity. Okay. This is an operation wherein the input sort of to this gradient is a scalar, and then the result will be a vector. You see how interesting our life has become now, because I have the potential V, correct, which is a scalar function which is easily measurable. From there I am actually able to determine the vector quantity electric field. Okay. In fact, this kind of method can be used in practice to map out the electric field lines of a given configuration. Okay. So, this is sometimes quite widely used. Okay. What does gradient of V max tell us? The gradient of a potential at its max will give me the magnitude of the electric field at any given point. Okay. It will give me the magnitude of any given point. In fact, this is very general. For example, let us assume that there is some scalar function f and I calculate the scalar function, the gradient of the scalar function. What will be the result? This will be x hat del f by del x plus y hat del f by del y plus z hat del f by del z. Okay. If I now consider some path, okay, say the path dl is given by can be decomposed into x hat dx plus y hat dy plus z hat dz, and then I ask you what is the component of del f on this line del dl. You can obtain that one by taking the dot product of the gradient with respect to the line segment, and you are going to get del f by del x dx plus del f by del y dy plus del f by del z dz. What is this quantity del f by del x dx? Now, del f by del x gives you the slope of the function f as you move along the x axis. Therefore, this is basically slope into change along the x axis. Similarly, slope into change along the y axis, slope into change along the z axis. Therefore, what this quantity is giving you is the total change in the function f if you had taken a directional path or a directional line along dl. So, if you go in a given direction dl, you can find out what would be the maximum, so you can find out what would be the change in the function value, and the maximum change will give you the maximum change in the function value, and this is what you are going to use if you want to climb a hill or go down the valley. Okay. So, we will stop the potential at this point. We will now introduce another important electromagnetic quantity and get to the Maxwell's first equation via Gauss's law.